Okay, we're going to go ahead and start our unit on chemical reactions. We're going to go ahead and just show you how chemical equations are set up and some signs of chemical reactions. This is the one of three videos that we'll be seeing this week. So just follow along through. If you need to pause as you need to go along, go ahead and pause and just kind of continue to go with us. So you should have kind of done a POGL first. I believe I have that scheduled for you, kind of working on seeing these reactions or these equations in action, and then from there I'm going to show you how to balance some of these equations in a separate video from this one. So the first thing we're going to talk about is a physical change. So a physical change is a change during which some properties of a material change, but the composition of the material does not change. So in other words, it the material itself or the substance doesn't change. So some examples of physical changes are cutting things, breaking things, grinding things, or tearing things. Like if you tear a piece of paper in half, it's still paper. It's not something different. If you cut your hair, it's still hair. It's not something different. So, a physical change is something that, changes maybe the visual outlook, but doesn't change the composition. Now, keep a note that phase changes are also physical changes. So you have melting, boiling, freezing, condensing, evaporating, so forth and so on. So phase changes are also considered physical changes, and also dissolving. Dissolving is a physical change because all you have to do is evaporate the water out and you can get the substance right back. So it's not like it transformed into something totally new. It was dissolved in water, or what we call aqueous. Okay, so for chemical changes, a chemical change is a change in which a substance undergoes a change in identity. So in other words, there's an identity change going on there. The composition has changed. The substance has changed into something new. So examples are burning, rusting, and decomposing. Those are all examples of things that once they have undergone that change, or once they've done that, they are now a new substance. Don't be confused with phase changes, okay? Phase changes are not chemical changes. Phase changes are not chemical changes, and dissolving is not. Those two are physical changes. Let's just make sure not to confuse the chemical with the physical. So burning, rusting, and decomposing are chemical. Okay, phase changes and dissolving, those are physical. All right, moving forward. Okay, just take note of some of these signs of chemical changes that are occurring. We've seen a lot of these in some of the experiments that we've done. Heat and light or gas has been given off. We've seen both of those in the reactivity lab and the flame test lab. A change in color or a change in odor. We saw that again during, at least a change in color during the flame test lab. A precipitate or a solid product is formed and gives you kind of a cloudy look. We haven't yet done that, but we will be doing something to that effect during this unit. Sound, we've done the hydrogen test during our reactivity lab. When we tested for hydrogen, got the little pop, whoop, when we put the flame underneath the test tube. And then bubbles, only if due to the chemical reaction and not due to anything else. So we have the bubbles there, except boiling. Boiling does not count as a sign of a chemical change, but if there is no heat present, or no external heat present, if the heat is forming just merely because of that chemical change happening, then yes, that does qualify as a sign. Okay, when signs of a chemical change can be deceiving, again, boiling, that does not count. A phase change from a liquid to gas is what happens during the process of boiling. Okay, that is not a reaction. That is simply a phase change from liquid to vapor state of water. You will see bubbles in that instance, however, but that is not a chemical change. Okay, it just turns from liquid water to water vapor. It's still water. Diluting, if you look here at this example, I use like McDonald's sweet tea or really high sugar content Kool-Aid, right? If you're diluting and you're adding water to lower the concentration, which we'll talk about more in the solutions unit, okay, that can alter the color. Like for instance, if you water something down or dilute it, it can affect the color going from dark to light. But again, that is not a chemical change. Okay, dilution is not a chemical change. That is as a fake out. Okay, the color is kind of changing, but it's because we're adding water, not because there's a chemical change or a substance change going on there. Now, if you look over here to the right, okay, this is a chemical change. You see you have two colorless liquids. Once you combine them in a test tube, it's forming this yellow substance, okay? That is a precipitate. That's what a precipitate is. The two clear liquids are making a yellow precipitate is a chemical reaction. So if you saw this, this would be an example of a chemical reaction. Okay, so chemical reactions are a chemical change in which new substances are formed. So let's make sure we emphasize that a new substance is formed in a chemical change, in a chemical reaction. And we represent that with chemical equations. So we use a symbolic representation of a chemical reaction by chemical equation. I'm going to show you a few of those. Okay, some terminology you just want to know before we get started is we have a reactant. All right, that's starting a substance in a chemical reaction. So for example, here it's A plus B. And then we have the products. So these are the substances produced in the chemical reaction. In this instance is C plus D. Also, you have a few things when we're looking at these compounds. You have the coefficients, which are the numbers that are in front, right there in front of the compound. Okay, that tells you the number of moles or the number of molecules or the units of a substance that you have present. The subscript, which is this little number here below in red, is a small number written below that tells you exactly how many atoms is in that particular compound, or it tells you the number of moles or atoms of a particular element in the compound. So for here for H2O, there's 2 hydrogen, and because there's no number outside the oxygen, there's 1 oxygen there in this H2O compound. 2 hydrogen, 1 oxygen. Okay, here are some symbols that you're going to need to know for these reactions. So when you're looking at the equations, you have a single arrow. That means yields or produces or results in. So this separates the reactants from the products. You have your reversible arrow, your double arrow, that shows a reversible reaction or equilibrium. You have your S, L, and G for solid, liquid, and gas. And then you have your AQ for aqueous, which is dissolved in water. And then you also have your sign with an arrow on it, your yield sign with an arrow on it. That means occurred by heating, or heating could have been a catalyst to that reaction to help speed it up. But then again, solid, liquid, gas, aqueous, and then you have your double arrow, your single arrow, and then your arrow with the triangle is with heat. Okay, so collision theory. This is something that we're going to revisit over and over and over again, so just make sure you kind of lock this in. Molecules must collide in order to react, okay, but they need to collide having the right orientation with enough energy. Both of those things are requirements in order to have the collisions necessary for the reaction. So if you look over here, and I know kind of covering some of this up, but with my webcam, but here it will be a proper collision. It needs to hit right there with a certain amount of energy. Okay, if it's backwards and hits right there, that is not going to be a collision that's going to cause a reaction. If it hits over to the side right here with the green side in, that is not going to be what's necessary to cause a collision. If it's hitting, with this white part in the wrong location, that is not going to be able to cause the reaction. So in order for these reactions to occur, the collisions have to be at the right orientation with enough energy to make the reaction work. All right. Now, all these equations are based on the law of conservation of mass. So we have all of these things based on the law of conservation of mass. So matter cannot be created or destroyed. That is the law of conservation of mass, universally known, still being studied, however, but matter is not created nor destroyed, just transferred from one thing to the next. So therefore, every chemical equation must satisfy this law. And so equations must be balanced so that the total mass of the reactants equals the total mass of the products, or the amount of atoms that we have on the reactant side is going to be equivalent to the amount of atoms that we have on the product side. Okay, so we can do a comparison of atoms, which we're going to do for balancing equations, to figure out how to do this. Okay, I'm going to go ahead and work out this example here for you and how the particular way is to balance an equation. So I just want to kind of go through these examples. Remember, in doing this, you can only change the coefficients. You can only affect the coefficients. So you can never change the subscripts in the compound. Now we know where they come from. They come from the crisscross, like right here. aluminum Al2SO4 or aluminum sulfate. We know this is the proper compound here because of the crisscross. If we look at the ions here for copper 2 sulfate, we know this is the appropriate compound for this particular crisscross to happen via bonding. And we know the names from nomenclature, so that's a review point there. But we have those examples, and I'll work that out on a separate sheet of paper and show you how I go about handling these balancing equations. Here goes some more of the example problems that I'll try to show you here. I'll work through these in hopes that it's good preparation for you to study and be able to handle on your own. These do sometimes take a while, so today, now that you've done your POGIL activity, you should be able to work on balancing these. But before you actually look at me balancing, I would like for you to pause in between each time you see me balancing the equation, so that you can make sure that you're going through the process first before you're seeing the resolution or the answer. So just make sure you're doing that. Okay, we're done for the day today. I'm going to go ahead and make sure you get your homework. Your homework is going to be the additional sheets that are given to you dealing with balancing equations. Take your time on that, work on that. If you have questions, please write them down. And if you have questions like going forward, we'll continue to get back to them. Just a side note here that this particular equation here is going to be one of the tougher ones that you're going to do. And I'll show you how to do that and how to manage that equation when you're working these out. Good luck, happy balancing, enjoy day one. You can work together if you need to. But any questions you have on this, I'll be glad to answer when we get back. Key is practice, practice, practice. Line them up, keep them in order. And I'm explaining this because I'm going to tell you how it goes. Keep them in order and make sure you're constantly updating your sides when you're making changes. Constantly update your sides until each side balances or is equivalent. And I'll show you how to do that in the example video. So good luck. And the first part, balancing equations. Welcome to second half of chemistry.